This video will contain some general rules to help us try to integrate more general functions. Alright, the scalar multiple rule is very similar as it was with derivatives. The integral of a scalar value a times f of x dx is equal to that number times the integral of f of x dx, again where we have a being some real number. So if we want to know something time the integral of something times a function, it's something times that integral. For sums, the integral of f of x plus g of x dx, the integral of the sum is the sum of the integrals. So this one is very convenient as well. So just as with derivatives, integrals are linear operators, we can separate out sums and scalar multiples. Alright, then our next rule is integration by substitution. So this is kind of the inverse of the chain rule for derivatives. So if we have some function, if we're integrating some function where it can be written as the derivative of f of g of x times the derivative of g of x, then the integral is f of g of x. So basically when we take the chain rule, we get this derivative. So if we integrate this derivative, we get the initial function back. So if we're lucky enough to figure out that we can factor our function in a way such that it matches this type of form, then we can get to this result here. Right, and integration by parts is sort of the inverse of the product rule for derivatives, although it's a little bit messier. So let's say we have the integral of u of x times dvx dx times dx. All right, so we have a function u of x, and we have the derivative of a function v of x, and we're going to integrate that product. So that integral is equal to u of x times v of x minus the integral of v of x du dx with respect to x. Okay, so we'll do examples of each of these and see how they work. So the integral of 12x cubed dx is equal to 12 times the integral of x cubed dx, which is equal to 12 times 1/4 x to the 4th, which is equal to 3x to the 4th. Okay, that's all good and well. The integral of 4 over x dx is equal to, well, 1 over x is the natural log, so 4 times that is 4 times natural log of x. Again, we're not worrying about the constants that usually come after for indefinite integrals. Not worrying about that. It is usually not of importance in physical chemistry. All right, the sum rule. Let's say the integral of cosine x plus 3e to the x dx is equal to the integral of cosine is sine. Integral of 3e to the x is 3e to the x. All right, that works out great as well. Now let's look at integration by substitution and how we do that. So let's say we have the integral of 2x e to the x squared dx. All right, so we're going to have to define what some values are. So let's say, so we have e to the u, so I'm going to say u equals x squared. So du equals 2x du, taking the derivative there. Equals 2x dx. All right, so now I can say that dx equals 2x over du. So now we're going to see why this is called integration by substitution, because I'm going to substitute in u for x squared and 2x over du for dx. So I'm going to have this integral equals, or sorry, this is du over 2 dx. Too far ahead now. Got to erase that carefully. All right, try this again. So we're going to have dx equals du over 2x. All right, so we have 2x times e to the u times dx is now du over 2x. Notice we have made a substitution for x squared. We have made a substitution for dx. All right, so what's going to happen now? Sorry, mess it up again. Du over 2x. If I could get this right, that'd be fantastic. All right, so 2x cancels with 2x. What are we left with? We are left with equals the integral of e to the u du. What is the integral of e to the u du? It is e to the u. What is e to the u? U is x squared. That's x squared. You'll notice if we take the derivative of e to the x squared, we will get 2x e to the x squared. So that's why integration by substitution is like the inverse chain rule, because we have to see something that looks like a function and then the derivative of the inside of that function. All right, last and not least, integration by parts. Let's look at the integral of x sine x dx. All right. So this is going to equal, well, let's define our function pieces here. We want something that looks easy to take a derivative of, or whose derivative is going to be basically 0, or something who's going to be easy to integrate. So what I'm going to define here is I'm going to say u equals x. I'm going to say v equals minus cosine x. So we're going to have du equals dx. We're going to have dv equals sine x dx. So now I just substitute in the parts here to get the result. Because x is u, dv is sine x dx. So now I need to multiply u times v, which is x times minus cosine, so minus x cosine x. Then minus the integral of v du. So I have minus the integral of minus cosine x, so minus times minus gives me plus the integral of cosine x dx. All right, so then this is going to give me the result that this integral is equal to minus x cosine x, and the integral of cosine x is sine x. So integration by parts is a matter of identifying which function is u, which function is dv, then finding v and du and substituting in the appropriate parts. So these aren't nearly as complete and satisfying as the rules for derivatives. We can take those 10 rules that I gave for derivatives and then take the derivative of any arbitrary function just by applying those rules in succession. But for integrals, it's more complicated. There isn't always an analytical result. It isn't always easy to find. So integrals are much harder to do in general, which is why we like to do things like Taylor series, because if we can express things in terms of polynomials, it's pretty easy to take the integrals of polynomials and find our answer.